Yeah, so welcome after the break. So we are talking about in fact, what we got, it is the generalized model of CE and CS amplifier here. What it is having here, it is the input signal source having the source resistance of Rs, and then signal coupling capacitor C1, and then if I consider this is the main amplifier, where we do have the input resistance represented by this R1, and then we do have voltage dependent voltage source, which means that this is the core of the amplifier, and then we do have the output resistance R2, and then C3 and C4, they are representing either C pi C mu or CGS and CGD based on whether the circuit it is CE amplifier or CS amplifier. So, this capacitor, it can be converted into two equivalent capacitance. One is for the input port, the other one is for the output port. And then the input port part coming out of the C4, it is what we said is that C4 multiplied by 1 minus AV, or in this case AV is equal to VO. In fact, if you see here, we are putting a minus sign here, assuming that the polarity of the voltage dependent voltage source here, it is positive. And on the other hand, so this is the contribution coming to the input port. Earlier we used to call say C1. Now, let me put a different name, C4 in, that means the input port capacitance coming due to C4. So, likewise the output port capacitance coming due to C4, let you call this is C4 out. So, this is equal to C4 into 1 minus 1 by A naught. So, if I consider this gain, it is very high, and in case if it is having minus sign here or the polarity here it is opposite, then we can consider that C4 in, it is just C4 multiplied by 1 plus magnitude of the voltage. So, this capacitance, it is coming in addition with C3. As a result, we are getting the net input capacitance C in equals to C3 plus C4 and then multiplied by 1 minus A naught. On the other hand, the output capacitance, net output capacitance, of course, we do have CL. So, the CL is coming as is plus this part, namely C4 multiplied by 1 minus 1 by A naught. Yeah, I like to mention one thing here. It is in the actual circuit, CE amplifier or CS amplifier, typically we do have one DC decoupling capacitor or AC coupling capacitor, and typically we used to name as C2, and then the C2 and CL, if I consider their typical magnitude, this may be in the order of say 10 microfarad, whereas the CL may be in the range of say 100 picofarad. So, as a result, the load coming at this node due to the series connection of C2 and CL, practically it is dominated by CL. So, that is why at this node or at this node, whatever the effective load capacitance we do have, coming out of say these two parts, it is getting to be equivalent to C L. Okay. So, that is why we are not considering this C 2 in this analysis. So, in summary what we have, it is at this node we do have the C in, and then at this node we do have the net C out. Now, to get the frequency response of this circuit, namely starting from this point till the primary output, what we have, it is we do have one network here, and then we do have of course, the main amplifier starting from this point to this point, and then of course, at this point we do have the C out. The board looks like clumsy. So, let me clear and then summarize it. What we have, what I said is that from here to here, the gain it is defined by A naught. In addition to that, we do have this resistance coming in series with or getting loaded by net output capacitance called C out. On the other hand, from this point to this point, if you see the circuit, we do have one R, we do have one C, and then we do have one R here, and then the effective input capacitance coming from C 3 and C 4 together. So, that gives us a network something like this. So, once to get the overall frequency response, we need to get the frequency response from this point to this point, and then of course, here to here. So, just to start with, let us see the first part, namely this part, and the corresponding circuit it is given here in this diagram. We do have the input signal, we do have the source resistance, we do have the C 1 in series, and then we do have the effective input resistance. In this case, you may call it is R 1, but whatever the resistance we may name as R in, and then C 3 and C 4 together, it is contributing to the net input capacitance with respect to ground, that is called C in. So, our first task is to find the frequency response from this point to this point, namely V 1 by V in, maybe in Laplace domain we can see, and then we can find what is the corresponding transfer function we are getting. So, in the next step, next slide, what we are going to do, we are going to analyze this R in series with C, in series with R in parallel with C. So, we do have this circuit, we do have R and then C and then R and the C coming in parallel. Now, if you see here, to get the frequency response of this circuit, namely in Laplace domain V 1 S divided by V in S, we can get the transfer function by considering this impedance, which is R in parallel with 1 by S C in, and then R S in series with 1 by S C 1 plus R in parallel with 1 by S C in. Now, the numerator part you can further simplify, and you can see that this is R in divided by 1 plus S R in C in, and in the denominator we do have R S plus 1 by S C 1 plus this part, it is same as this R in divided by 1 plus S R in into C in. Now, if I further simplify, so this factor, once it is coming in the numerator, it is getting cancelled with this factor, but then we do have S into C 1. So, that gives us in the numerator we do have S R in C 1, and in the denominator we do have all these things getting multiplied. So, what we do have S, this R S multiplied by S C 1 multiplied by 1 plus S R in C in. So, that is the first term, and then we do have the second term, where we do have 1 plus S R in into C in, and then we do have the third term, which is S R in into C 1. So, in the denominator we do have of course 1, and then we do have the S term we do have here, and also we do have here. In addition to that, we do have a square term as well. So, in the denominator, if I further expand it, what we are getting is that numerator is remaining S R in into C 1 divided by 1 plus S. We do have R in into C in plus we do have R in into C 1, and then also we do have S into R S into C 1, and then we do have A square into C 1, C in, R in and R S. Right. So, the transfer function here, which is written here, you can see that it is having a 0 here due to this S term, and also since it is second order polynomial in the denominator. So, we are expecting 2 poles. Now, let me consider a typical numerical value, and based on that we make some assumption here. So, what we have here, it is C in, which is typically much smaller than C 1. So, probably we can ignore this part, and then we can consider this term, and then we can take C 1 outside. So, in the denominator, if we do this approximation, we do have S R in and then C 1, that is coming in the numerator, and in the denominator we do have 1 plus S, then R in plus R S into C 1, and then we do have the A square term, coefficient of A square, it is given here, which is R in into R S into C in into C 1. In fact, this can be well approximated by considering 2 factors, and if I consider typical value, again we can do some assumption, valid assumption to simplify the denominator, and what we can get, that we can get 2 factors. One factor is coming from here, namely 1 plus S into R in plus R S into C 1. So, this is the first factor, and then the second factor, it should be such that the coefficient of A square should match. In fact, that can be shown that the second factor, it will be 1 plus S. So, then we do have R in, then R S, divided by R in plus R s into C in. Okay. So, in fact, if you multiply, of course, there is an assumption that here this term, of course, along with this term we do have one more term which is 1 multiplied by this part, but we assume that term it is very small, and then product of this s term and this s term, it is matching with this. So, here we may say that the first term it is giving a pole called P 1. So, we can say that P 1 it is coming from the first one, and the location of the pole it is minus 1 by R in plus R s multiplied by C 1, and then the second pole P 2 it is coming from the second factor, and it is given by minus 1 divided by R in into R s divided by R in plus R s multiplied by C in. In addition to that, this since we do have the s term here in the numerator, we also have a 0 at 0 frequency. Okay. Also, if you see that in the mid frequency range, what may be the attenuation? When I say mid frequency, what does it mean is that if you consider the coefficient of s is dominating over this 1 and s square term, and if I say that if this is dominating, that means if I drop these two part, then what we can get in the numerator, we do have R in and C 1, and in the denominator we do have R in plus R s into C 1, C 1, C 1 it is getting cancelled, S is getting cancelled. So, we can say that mid frequency gain, if I call say whatever it is A defined by V 1 divided by V in mid frequency, that is coming R in divided by R in plus R s. Let me explain the intuitive way of analyzing this circuit. What we have, it is the frequency response. Let me use this space. The frequency response, if you see, okay, probably I can use this space. No, let me use this space. So, if I say that the gain of this circuit, it is so this is the frequency in log scale, and this is V 1 divided by V in dB. So, in very low frequency we do have a 0, and then we do have pole, and after that the gain it is getting stabilized. That means, this is the attenuation, and that attenuation is given by this R in divided by R in plus R s, and then we do have the second pole. So, we do have the first pole here P 1 given by that expression, and then we do have the P 2 given by this expression, and it starts with 20 dB per decade slope at the beginning, which means that it is having a 0 at 0 frequency, and this attenuation it is essentially R in divided by R s plus R in, and this need to be converted in dB. Okay. So, now coming to the intuition, in very low frequency, this capacitor it is blocking this signal to propagate here. So, that is why we do have lot of attenuation here, but then with progress of frequency this capacitor it starts allowing the signal to come to this node, and that is what the indication that as we are increasing the frequency the signal it is propagating here. And then we do have a situation where this capacitor almost it is working as a short, and leaving behind we do have only this R s and R in. This capacitor yet to show its effect. So, in the mid frequency range what we have it is R s and R in series. Input we are applying at this node, and then the output you are observing here. So, if you see this circuit, of course, the attenuation from this node to this node it is defined by R in divided by R s plus R in. So, that is what the attenuation we are getting here in the mid frequency range. Now, once we have this circuit, so entire portion it is working as a Thevenin equivalent signal source, and its Thevenin equivalent resistance now it is R s in parallel with R in, right. And then we do have the C in connected here, right. And this signal it is not just V in, it is attenuated version of V in. So, I should say this is V in multiplied by R in divided by R in plus R s. So, from this frequency onwards this is the model, and then based on this resistance R s in parallel with R in and then C in we do have a pole. So, that is why the expression of this pole if you see it is coming from this resistance which is R in and R s in parallel, and then we do have the C in. So, that is why the pole we do have here. So, that is the interpretation of this frequency response. So, in summary what we like to say here it is the frequency response of this circuit starting from this point to this point is given by so this is the frequency, maybe we call it is radian per second, and then we do have the gain in dB. So, this is in log scale, typical Bode plot, right, and at very low frequency we do have a 0, and then we do have a pole where this capacitor it is just sorting the signal beyond that frequency, and then after that this capacitor it starts sorting the signal creating a pole here, and location of this pole and this pole as I said this is 1 by R s in series with R in multiplied by C 1, and location of the other pole it is 1 by R s in parallel with R in multiplied by C in. So, that is the frequency response of R c in series with parallel connection of another R c, and this attenuation it is we should say this value. So, this is the 0 dB level. So, this value it is minus of course, it will be coming minus, but let you write the expression 20 log base 10 R in divided by R in plus R s. Now, we shall use this frequency response for our frequency to get the frequency response of the CE and CS amplifier considering the high frequency model of the transistor in the next slide. Okay. So, this is we are coming back to the generalized equivalent circuit of the CS amplifier, which is given here, and from this point to this point we got the frequency response, and then from here to here we will be getting another part of the network, and hence we can get the frequency response starting from the primary input till the primary output. So, to start with, we already have discussed that if you consider say V 1 by V in, and we obtain the corresponding frequency response like this. So, this is V 1 by V in, and we already have discussed the location of the pole, and then we do have from this point to this point, or say this point. So, we can say V 2 by V 1, and that is defined by this A naught. So, this A naught, it is pretty high. So, we can see that A naught, it is constant. So, this is V 2 divided by V 1. So, if I combine these two, so what we can get, it is that V 2 by V in. So, V 2 by V in, if I plot V 2 by V in, it will be similar to this one, but it got lifted up. So, this is the V 2 by V in, and then V 2 to V out, we do have another RC circuit, and that RC circuit, of course, we do have the resistance here, we do have the capacitance maybe primarily coming from the load capacitance, and maybe some part of the C4, it is also contributing to the C. So, if I consider on the other hand V 2 to V o, so there what we get, it is of course, here to here it is passive network. So, it is starting with almost 0 dB, and probably it is having a pole like this, right. So, this is V o divided by V 2. Now, if I combine say V o by V 2 and this curve together, so then we can get the overall frequency response. Let me use different color here, maybe black color. Yeah. So, to get V o divided by V in, that is the complete overall frequency response. To do that, I need to combine this curve and this curve. So, that V 2 and V 2 are getting cancelled, we do have V o in the numerator and then V in the denominator. Since it is having this curve, it is having 0 dB here. So, I should say this is not disturbing. So, this characteristic curve, it is supposed to be same as like this, and then it will be coinciding like this, and then probably we do have the pole here, second pole. So, this pole. So, now we like to say that the location of this pole. So, the net frequency response now we obtain, it is like this, and so this is the overall frequency response, blue color. And location of this pole P 1, it is coming from this network, initial network. You may recall its expression is 1 by R s in series with R 1 and then we do have the C in, and C in we have seen that C 3 and C 4 they are contributing. This pole we say that P 2, which is R S in parallel with this R 1, earlier we used to say that this is R in, that is multiplied by, sorry, this is not C in, this is rather C 1, and here we do have the C in. And then also we do have the other pole coming from this network, and this pole, it is, we may call this is P 3, and that is defined by this R 2, and the net capacitance at this output node, probably this may be C L, and then contribution coming from the C 4, and that may be C 4 multiplied by 1 minus 1 by A naught. And all practical purposes you may consider this is 1 by R 2 C L plus C 4. Okay. So, this is typically what the frequency response we do expect, but of course, it depends on the numerical value of the different components. Say for example, in case if this this pole, third pole, if it is appearing before the second pole, which means that if this violet color instead of having a pole here, if it is having a pole somewhere here, then obviously, if I call say this is the possible situation, maybe say this is P 3 dash, and then if I combine this pole or rather this frequency response with this one, and if the location of the third pole it is here, which is before this one, obviously that will define the overall frequency response having a pole here. In other words, the lower cutoff frequency typically it is coming from this one. So, we may say that omega lower cutoff frequency, it is defined by P 1. On the other hand, the upper cutoff frequency it is defined by minimum of this P 2 and P 3, whichever is minimum. So, that defines the upper cutoff frequency. So, in our numerical example, so we will see that two cases where for one case maybe this P 2 is lower, in the other case maybe the P 3 is lower. So, probably with that numerical example things it will be even clearer. So, we are going to talk about numerical examples, but before that let me take a short break and then we will come back.